Hi, Daniel. Thanks so much for joining me today.
Absolutely. It's a pleasure to be here.
You spent more than 15 years developing ion mobility and MS technologies. What originally pulled you toward analytical instrumentation instead of pure chemistry?
Yeah, in my undergrad studies, I majored in chemistry, but got a minor in math. So analytical chemistry was basically the sweet spot where I could combine both of those skill sets. And I really love the idea of being able to apply a fundamental understanding of chemistry to make measurements of things we can't see with the naked eye. And then you couple that with I've always had an interest in how mechanical things work and have these stories about taking things apart and putting them back together, and sometimes having leftover parts and finding more efficient ways to put it back together. And so that was the evolution of my intro to analytical chemistry. And when I was looking for different graduate schools and interviewing with potential advisors, I remember walking into Dr. Emil Schweikert's lab at Texas A&M and seeing all these shiny metal vacuum chambers and electronics with wires running everywhere. And I was just hooked. And his lab had no commercial mass specs, and they developed every system custom from the ground up. And I wanted to learn how to do that. And so it's exciting to think about building your own tools to make chemistry measurements of these molecules that I'd spent so much time thinking about and learning about in books, but it really put it into perspective to be able to build the instrumentation that allows you to make physical measurements of the world around you. So that's really what I see in analytical chemistry is being able to measure what's there and how much of it's there, and to be able to build the tools with your own hands to do that is really what gets me out of bed in the morning.
And I believe you received your PhD at Texas A&M, so you moved through both academia and industry. How did that shape how you approach product development today?
Yeah, so I got my PhD at A&M, and then I did some research at Florida International University, and then moved on to industry. So I've had a couple of roles at startup companies in analytical instrumentation, but I think it was really helpful coming from academia, where you don't have all the resources and the specialization that you often have at companies where, oh, you're a mechanical engineer, you're an electrical engineer, that's your job as a grad student, and then as a researcher. You kind of have to be everything that you need in order to get things done. And so it allows you to develop a lot of different skills. And so I had this opportunity, crazy opportunity, I realize now, to basically go at it and single handedly design these instruments and learn the mechanical design, the electrical design, the software coding necessary to make modern instrumentation. And so it gave me a lot of opportunity to make mistakes, but to explore different areas in engineering and science. And I had the space to make mistakes. So I learned a million ways to do things wrong. And now I can lean on that as experience going forward in my current role to say, whenever I'm in a design review, I've made this mistake before. You might not want to do it that way. And so that's really been beneficial. And I think that experience of having to do everything myself has really helped me in relating to everybody that I interact with on a day to day basis, where I've at least got that common language and understanding of what they're trying to accomplish in their role, and be able to communicate my experience in a way that's going to help them do their job better.
And I believe you joined MOBILion in 2018. So I was curious to hear from you what problem felt most urgent to solve from a company standpoint.
Yeah, so 2018, since then it's been a wild ride at MobileIron. We are a venture capital backed startup company. And so basically that means that you've got investors that give you a bag of money and say, hey, go make more of this stuff. And our mandate was basically to take a technology that the investors had licensed from Pacific Northwest National Laboratory and convert that into a commercial product that could be sold. And so when I showed up, there was a prototype sitting in the laboratory that had literally exposed voltages. You couldn't touch the vacuum chamber. It was floated to like 200 volts. And so a safety hazard, and it was a giant machine. It wasn't nice to look at. And they said, as quickly as possible, you have to redesign this whole thing into something that a normal mass spec lab can handle, and something that is scalable, reproducible, reliable, that you don't have to stand on one foot and wiggle your nose to get it to put out results. And so it was a daunting task, but we had an incredible team of scientists and engineers, and we were able to pull that off in about 18 months. And so that was the most pressing thing, is how are we going to take this Frankenstein prototype and convert it into something we can actually send out into the world and have people be successful with. And it was really that opportunity where, again, the skills I developed earlier on in my career, I was able to jump in. It felt like just a cog going into a system that immediately meshed with the other gears and was able to make forward progress and hit the ground running.
So this is actually going to be the 50th episode of concentrating on chromatography, which I'm very excited about.
Congratulations.
Thank you. I don't think most podcasts don't make it to episode 10. I don't think so.
That's right. That's right.
Happy about that.
You stuck with it.
Absolutely.
Had some success.
Yeah, still going. Well, I'll reevaluate at 100, but
there you go.
We're in it. And certainly we've spent a lot of time on this podcast talking about LCMS. And certainly I assume that that's a popular frame of reference for a lot of people. How would you explain SLIM, structures for lossless ion manipulations, in plain language to those people who are more familiar with LCMS?
Yeah, so SLIM is the technology I referenced that we licensed out of PNNL, and it is an ion mobility technology. And what that means is that we're creating ions like you do in mass spec. You have an ionization source, and then we're doing a gas phase separation of those ions. And it's interesting how there are a lot of analogies to what you think about in terms of chromatography, where we can translate that into what we're doing in the ion mobility world. So we talk about things like peak capacity, and instead of retention time, we talk about arrival times of ions. We also have an analogy to gradient elution. So when you're changing your gradient mix, your solvent mix, we can ramp our voltages that we apply and achieve a lot of the same tricks of making chromatography better, but we do it in the ion mobility space. And so I would really think about it as another type of chromatography, just that we're doing it on ions with voltages instead of achieving that separation based on a stationary phase and a mobile phase. So that's really the best corollary. And the way that we do SLIM is often integrating it with LCMS. We're plugging this additional method of separation into the instrumentation between the LC separation and the mass measurement. And so the instruments we're building are LC ion mobility mass spectrometers, and adding that technology into the workflow provides a number of advantages in the measurements we can do. And just one other corollary to chromatography is we think about chromatography is driven by the kinetics of the interaction of these molecules in the liquid phase. And because we're doing the separations in the gas phase, the kinetics are different. It's the gas versus liquid effect, where the separations we can do are actually 1,000 times faster. So if you're normally doing a 20, 30-minute LC run, that same type of a separation we can often do 1,000 times faster. So it's on the time scale of milliseconds to seconds. And so it's nice how that meshes, and we're able to still do the full resolution LC data collection and then collect these slices in the ion mobility domain to add this additional dimension of separation.
And I believe you just briefly referenced this, but how is SLIM different from traditional ion mobility approaches like drift tube or TIMS?
Yeah, so there's a long history of ion mobility and a lot of other approaches to it out there. And over the years, people have employed those techniques in similar ways to what we're doing with SLIM, but there have been certain limitations in terms of either the resolution that you can achieve with those other techniques or the sensitivity that you can achieve, transmission efficiency. How many of the ions I put in on the front end actually make it to the back end? And so whenever the SLIM technology was developed at PNNL, all those researchers out of Dick Smith's lab were aware of these other ion mobility technologies. But the story goes that they locked themselves in a room and said, we love ion mobility. We all love this idea of being able to separate things 1,000 times faster, but we don't want to sacrifice the resolution or the speed. Can we come up with a way to control ions that doesn't have those trade-offs and those sacrifices? And so that is really the main difference, is that we've been able to demonstrate with SLIM, building on the work of PNNL, that you can get near perfect transmission of ions through the device, and that it's scalable, and you can achieve resolving powers that are over 2000 in the mobility dimension. And so you can tell the difference between incredibly small differences between molecules, things like isotopomers, which, if you're not familiar with that, I can take a carbon-13 atom and move it to different parts of the molecule and separate a molecule that has the atom on this side versus that side. And that would not be distinguishable by chromatography or mass spec, but ion mobility has the capability to differentiate between those small changes like that if you have enough resolution.
And the phrase lossless ion manipulations is very intriguing and exciting. In this context, what does lossless actually mean in practice?
Yeah, so the idea that what I put in on the front end, I want to get out on the back end is the general concept. And I think has been a really helpful acronym for us because it allows us to, like you said, differentiate from previous ion mobility technologies that weren't lossless. And so that's kind of the thing you want to jump out in front and say, okay, we've got a new ion mobility technology. This is why you should listen, because it's not losing ions like you're used to with ion mobility. And so we've done a lot of work to demonstrate that in a bunch of different ways so that people will actually believe us when we say that. And so a couple of the examples of that is whenever we integrate SLIM with a commercial mass spectrometer, one of the tests that we do is measuring the sensitivity of that system before and after we integrate SLIM. And we're able to demonstrate now on multiple different vendors, multiple different types of mass spec, that we can integrate SLIM, pass ions through meters worth of path length that wasn't there originally in the instrument, and still maintain the original sensitivity specifications. And so we're not losing any of the ions in the process of analyzing them.
That's very exciting for sure. You make a bold statement that the problem is the quadrupole, and that's almost heresy in tandem MS.
Mm-hmm.
What's wrong with how we isolate precursors today?
Yeah, so this is another example where, in order to explain how impactful this technology is, we have to be bold. And so, if we think about what we're doing in LCMS with the quadrupole, if we're talking about a high res system, we've got a tandem mass spectrometer that allows us to isolate precursor ions and then fragment them and then measure the resulting spectra. And that process is tried and true. It's served us well for the past 50 years. But are there limitations that imposes? And there are a couple that we have uncovered, and we believe that we can surpass that performance by using the SLIM technology and a new mode of operation we call parallel accumulation mobility aligned fragmentation, or PAMAF for short. And the main limitations of the quadrupole are, number one, it only separates based on mass to charge, right? And so if you have different molecules that have the same molecular weight, those are going to be co-isolated by the quadrupole. And then if I go through this process of fragmenting and detecting the fragments, I'm going to have chimeric spectra. And so I've got now a spectrum that contains fragments from two different ions, and I have to figure out how to separate those and identify them when I've got this overlapping spectrum. In the mobility separation, we separate based on size to charge rather than mass to charge. And so there's an opportunity for these isobars or isomers to be resolved in the mobility dimension. And then when we fragment and we detect the fragments, we can now generate clean fragmentation spectra that are unique to each of those precursor ions. So that's one example of how we can surpass a limitation of the quadrupole, but there's a couple of others in terms of the efficiency of that process. So when we look at different mass spec systems, tandem mass specs in the field, one of the most important metrics is how fast they are. And that's always a spec that's on the spec sheet of 50 hertz MSMS, or with the latest generation systems, high-res systems, you can get up to 200 or 270 hertz MSMS. And so that specification is really important because it's how quickly, how many of these precursor ions can I analyze in a given chromatographic run. And so what's important to remember is with this, you're determining that speed based on your quadrupole. And the quadrupole electronics have a certain time that's required to get from one set point to another set point and then to stabilize before you can make that next measurement. And that's what drives the speed at which the quadrupole can operate. And so that whole premise is dependent on how fast your electronics are and your quadrupole design. When we instead replace that quadrupole functionality with high resolution ion mobility, we are now able to separate and introduce these precursor ions at a much faster rate than the quadrupole. So we've been able to demonstrate, and it's now published, that we can go over 1300 hertz, so over 5 times faster than the current fastest high-res mass spec systems, and generate these MSMS spectra that are cleaner and more abundant at a faster rate. And that's because each of those mobility packets that we're creating by separating in the gas phase are only about 2 milliseconds wide. And so they're being introduced to the collision cell and the time of flight mass spec at a very high rate that is faster than what the quadrupole can achieve.
One thing that really stuck out to me was that you mentioned that quadrupole windows throw away 99% of ions. Where is that signal actually going?
Yeah. Well, if you've operated a mass spec for any length of time, there's maintenance required. So you have a PM, you have a service engineer that comes in, and if you're running relatively dirty samples, when you're throwing away 99% of those ions, they're going onto the quadrupole rods typically. And so that's what that service engineer often comes in your lab to do, is to take your instrument apart and scrape all of those wasted ions off your quadrupole rods. So the quadrupole is by definition a filter, right? And so it allows some stuff through, but it filters 99% of the stuff out, right? You're often selecting a very narrow mass range, and you want those precursor ions to be pure when they come through, but that means that all the other stuff has to be discarded. And that's another advantage of the high resolution ion mobility technique, is that we're separating things in time rather than filtering out the stuff we don't want to look at a particular point in time. And so by operating in a different way, we can go from throwing away 99% of the ions to allowing near 100% of the ions through and just relying on detecting them at different points in time.
If you could redesign MSMS from scratch today, would you still include a quadrupole at all?
Yeah, good question. So I've been on this bandwagon of abandon the quadrupole, but that's really just the attention grabber that allows you to open your mind and think about the measurements that we're doing and how to do it in a different way. There certainly still is utility in the quadrupole. And with complex sample analysis, you want as many tools as possible to get as specific as possible about what you're detecting. And that specificity will translate to improved confidence in what you're identifying and quantifying. And so we have a mode of operation, PAMAF, that allows us to not use the quadrupole at all, where we just transmit ions, all the ions through it, and rely on mobility. But there's also alternative modes of operation where we can incorporate the functionality of the quadrupole as well. And so why not take advantage of this pre-separation and mobility, where now we have sequenced all of the precursor ions, and when they're going to arrive, I can take advantage of that if I include the quadrupole in that workflow. Because now I know what's coming when, and I won't be throwing away 99% of the ions. I can allow a larger portion of them through while still achieving a mass isolation in addition to the size to charge isolation that we do in mobility. So, long answer to yes, your question, I would still include the quadrupole.
In your positioning high res ion mobility almost like gas phase chromatography. Is that a fair analogy?
I think the ion mobility translation to chromatography is helpful from a learning perspective and imagining what's actually happening. It is very similar to a chromatography or even a capillary electrophoresis separation, even more so. The gas phase is helpful because we're accustomed to thinking about gas phase chromatography often being faster than liquid phase chromatography. And we can leverage a lot of the same concepts in ion mobility. I would say the difference is that because we are separating ions using electrical potentials, it's a little bit different because you're applying a force to the ions directly rather than having those molecules driven through a stationary phase with a gas. And so is the gas driving the molecules, or is it the charge on the molecules themselves? So it's a little bit inverted from gas phase chromatography, but it is a fair analogy.
And I suppose similarly, again, mostly for the chromatographers listening, should we think of HRIM as adding another orthogonal separation dimension similar to 2D LC?
Yeah, I think in certain contexts, 2DLC is a great springboard for thinking about how ion mobility is integrated, both from a physical, I'm getting an additional dimension of separation capacity, also to a data structure of how to visualize in your mind. When I see a heat map or a two-dimensional plot of intensities, what does that mean? And interpreting the data that's coming off the system. The other caveat to that is that there are opportunities to, for certain workflows, replace the LC separation altogether. And we can just do ion mobility mass spec measurements. And so there it collapses to a single dimension of LC that we're replacing. But then also we can think about just taking slices through the data or collapsing different parts of the data. So we don't always want to rely on trying to visualize four dimensions of separation in interpreting our data, because that gets complicated and you don't always need the full dimensionality in the LC or the ion mobility in order to gain the necessary specificity for a sample. And so 2D LC is great for thinking about LC, ion mobility, mass spec in its full four-dimensional glory, but we don't always have to go to that level in order to get what we need out of the data.
The claim that LC gradients can be dramatically shortened is huge. How does mobility separation let you safely compress that chromatography time?
Yeah, so what we've seen working with our customers is that when you do LC method development, often you're working to identify the challenge compounds. So you've got two or three compounds that you're targeting oftentimes that are really challenging to separate. And so you're optimizing your method based on, I got to get baseline separation or at least some separation between these two peaks. And in order to do that, I have to go to 30 minutes or I have to go to 60 minutes or 90 minutes in order to get that resolution. If we can achieve separation of those components in the mobility dimension, you've now relaxed the requirements for your chromatographic method. And that's really the opportunity we have to now shorten the chromatography because we're getting that separation in another way. And you can still maintain the same level of quantitative performance without the long chromatographic run.
I'm very interested to hear where you are seeing the strongest adoption first. Is it potentially discovery proteomics or biopharma characterization or something else?
Yeah, so we currently have our commercial product Mobi that I talked about earlier, and that is really designed for the biopharma space and also has applications in environmental analysis and food and beverage analysis. And so it's hard to pinpoint exactly where we've seen the strongest adoption. We've seen application in a lot of different areas. It's kind of like asking the question of what is mass spec used for? It is used all over the place. And so we've been able to demonstrate value in a lot of different applications. It's more separations technology that can be applied to a lot of different problems. It's hard to pinpoint exactly one, but we see a lot of application in a lot of different areas.
Yeah, that's definitely a cool thing about having the podcast that focuses on separation science broadly. And even if I'm mostly focused on chromatography mass spec, it just applies in so many different functional areas where you get to talk about all sorts of different topics.
That's a fun part of my job is approaching it from this technology point of view and then applying this to different areas. And you get to talk to people from, from the EPA, from the FDA, from biopharma companies, and all these different areas, and talk to them about what is the challenge that you're facing in your analytical workflows. And you get to learn more about the chemistry of developing drugs or about we've got a customer that is making stevia, right? And crop harvesting and analyzing how do I grow crops that make the best stevia. And so all of these, how do I make my workflow faster? How do I get more sensitive? I've got interferences about how to twist and turn the technology to address limitations in each of these different areas and different applications. It's a new puzzle every day, but I'm using the same erector set to address it. So I really like that concept.
Yeah, and speaking of analytical workflows, how does this technology help simplify existing workflows that might require multiple instruments or multiple LC methods?
Yeah. So we talked about this a little bit earlier that one of the pain points in current LCMS workflows is the chromatography. It is hard to do that reliably, robustly, day in and day out. And we put a lot of pressure on the chromatography to separate these compounds. And because chromatography is so dependent on physical characteristics of the column that you're using, of how did somebody make their mobile phases? Did they use the same amount of additive? Is the temperature controlled correctly on the system? So you see a lot of issues with robustness in chromatography that whenever you are less reliant on getting really good chromatography, you can relax those requirements of how tight my retention time bands are. And I instead rely on the mobility separation. And in the case of mobility, we're able to achieve precision of like better than 0.25% is our spec. And so if you think about what it would take to achieve that in a retention time context, it is basically unachievable, right? And so when we think about making these mass spec measurement, LC mass spec measurements easier to reproduce in other labs, if we can translate that separation requirement into the mobility domain, it becomes much more translatable where we can do our method development on one system, and then we can deploy that to a number of other systems. And you can guarantee that your arrival time is going to be spot on with what we saw on the development system. And so that translatability makes it much more accessible for a larger number of people.
And how does peak capacity around 100 compare with what people expect from LC or quadrupole isolation?
Yeah. So I think that 100 number comes from an article last year specifically talking about proteomics. And so in that context, we're basically saying that if you look at the peptides we normally get from a protein digest, that in the mobility separation that we have in SLIM on a 13-meter long separation path, that is about 100 peaks that we can fit in that separation dimension. But I do want to point out that we've demonstrated if you have a larger range of sizes of ions that you're analyzing, we can actually achieve peak capacities over 300 in the mobility dimension. And so I just wanted to throw that out there. The peak capacity that we get with a 13-meter SLIM separation is typically on par with what you get in LC from a 20 or a 30-minute separation. So this is that 1,000 times faster, right? Where if you need a peak capacity of 100, it normally takes you about 20, 30 minutes in the chromatographic domain. And we get that same separation in a couple hundred milliseconds. And then comparing that to quadrupole isolation, I think a helpful context there, again, in proteomics, data independent acquisition is really important for discovery proteomics. It allows us to the whole proteome and detect a large number of proteins from biological mixtures. And in order to achieve that type of separation, typically researchers operate the quadrupole in a certain way where you have a little bit wider isolation windows so that you can transmit more of the ions and get through the full mass range that you want to isolate and fragment in a reasonable amount of time so it's still LC compatible. In that way, you can think about a peak capacity of the quadrupole. And the math that I like to do is if you're talking about proteomics, you're talking about a mass range of about 1,000 mass units, so from 200 to 1,200. And if you're isolating with a DIA quadrupole window of 10 to 30 mass units, that's where we get to thinking about a peak capacity of around 200 to 1,000 on the upper end. And so with our mobility separation of a peak capacity of 100 to 300, we're getting into that range of what the quadrupole is providing you in a DIA context. And so that's kind of the high level math that says, okay, now with SLIM, we've got an ion mobility technology that's providing a similar level of isolation specificity to what you're already getting on the quadrupole. And that's why we can think about jumping over and using the mobility dimension instead.
Now, I know this is somewhat of a big question, but you've sold me on the benefits. What are some of the trade-offs that a lab should realistically consider, whether that's the cost or sensitivity or complexity?
Yeah, good question. So I think it's kind of in the same category as 2DLC in a lot of ways, and that there are a lot of benefits to 2DLC, but along with that comes complexity in how you actually do the measurements and how you're going to process the data. And so that's the two areas that I would think about is employing another dimension of separation as part of your workflow. You really need to understand, what am I trying to get out of this? And that's a lot of what I do and our company does working with our customers is understanding their current methodology. And then when we apply ion mobility to that, what are we trying to address? Are we trying to get more sensitive? Are we trying to improve sensitivity? Are we trying to improve robustness? And then we can help them with that translation of method development so that we make sure that they're going to be successful in their application. And so that hurdle of coming up the learning curve of what is SLIM going to do for me and how do I apply it, we try and help our customers do that today. And then I would say the other challenge that is often an issue is data processing. So now I've got this additional dimension of separation. How do I handle that? Can I use my current software workflows to handle that same type of data. And in many cases, the answer is yes, but it often you have to click different buttons, and there's another learning curve there.
Daniel, talking with experts like yourself, I always like to ask a few questions about what the future looks like from what we can see today. So, 5 years from now, what does a standard LCMS workflow look like if mobility does become central?
I think that is a strong possibility. We've already seen significant inroads in terms of the acceptance of ion mobility. And where it's having an impact now is more on high end instrumentation. So in discovery proteomics now, the Bruker timsTOF is kind of a household name. I would say that that has really been demonstrated as the first scalable ion mobility mass spec technology. And now anybody that has timsTOF in their lab is using ion mobility. And so already this transition of LCMS to LC ion mobility mass spec is happening. And I think it's only going to grow from here. What I would like to see in the next 5 years is for that ion mobility capability to translate into less demanding workflows. So I talked about how high resolution ion mobility can be employed to improve the performance. And so those top end systems, that's what they're driving for. They need that performance. But there's also an opportunity to translate high resolution ion mobility into usability or robustness, which is more often a concern on not the top end instruments, but the more workhorse routine analysis tools. In particular, we've done a lot of proof of concept work integrating our ion mobility technology with triple quads, which right now there's really limited application of ion mobility to triple quads. And I think that that could have a really big impact on making quantitative analysis with LCMS much more robust, reliable, and reducing the training barrier of how to get good mass spec results.
Yeah, and based on that answer, I think I can predict what you'll say for this next question in terms of for high res ion mobility. You eventually see that more coexisting, let's say, rather than replacing quadrupoles entirely.
Yeah, I think in most cases the quadrupole is going to stay and we're going to supplement that. But there are certainly opportunities thinking about this from a instrument designer perspective. It is performing a lot of the same functionality. And so we often think about optimizing a system for size, weight, and power and cost, all of these factors, so that we can deliver a fit for purpose instrument for a particular customer or a particular workflow. And so I think there will be opportunities to entirely replace the quadrupole and reduce size and cost by leveraging this high resolution ion mobility technology. I don't think that that is necessarily going to be most of the instruments. I think we're still going to want the quadrupole, but I wouldn't rule it out.
And earlier we talked about some of the adoption areas. Just out of curiosity, outside of proteomics, what applications excite you the most?
Yeah, so I think metabolomics is probably another area where ion mobility is recognized as a really good answer for some of the challenges that they face. Proteomics is a little bit unique from an application perspective because it is a sort of pattern recognition for the identification and detection of proteins. You know, the all of the work that's been done in genomics to identify the proteins that we should expect from DNA has really paved the way for proteomics to grow the way that it has. So we know that if you use trypsin to digest your protein mixture, that you're going to end up with tryptic peptides, and we can predict what those ions are going to be even before we do the experiment. And then we're just looking through the data trying to find those peptides that we expect to be there. In the case of metabolomics, it's a whole different ball game where metabolomics is complicated because every body's biology is a little bit different. And we know the typical metabolomics cycles and the common metabolites, but whenever you venture into the world of untargeted metabolomics, you have this huge dynamic range. You don't have the predicted ions that you think are going to be there. You're really trying to, it's unknown unknowns. And having another technology that you can throw at this where you can improve the confidence of identification is really essential. And then you layer on top of that the advantages of speed and sensitivity. I think that metabolomics is going to be really a new growth area that will start to see the value of ion mobility even more.
And to rip up the script for just a moment, one thing just based on my daily work that I could see as a little bit challenging is so much of it, the environmental space relies on triple quad. So I'm not sure if you see that as a challenge just in terms of application areas.
Yeah, absolutely. So we've got customers that are using our systems in environmental applications, and a lot of the challenges that we see in metabolomics are the same in environmental, right? It's unknown unknowns and trying to um, track and monitor these analytes out of, you don't know what's in the environment in many cases. And so um, in the case of environmental analysis, there's in untargeted workflows, the triple quads usually turn up in the targeted workflows where the goal is boosting sensitivity and improving the confidence of quantification. And there are demonstrations where we can use ion mobility to achieve those goals as well. And so I do think that there are opportunities in environmental coupled to triple quads leveraging ion mobility, and would be loving to explore that with you.
The main listeners of this podcast concentrating on chromatography are current students, whether they be undergraduate or graduate students. For those people listening who are interested in this area and potentially want to work in next gen MS tech, what skills should they be developing now?
Yeah, this was me in grad school. I really knew that I was interested in developing mass spec technology and instrumentation. And it was challenging to kind of access the expertise and the knowledge and the skills that you need to design a mass spec from the ground up. But I think that's changing with the way that the mass spec field has gone the last 5 or 10 years. I think that information is getting a lot more accessible. I mean, we've got the Chat GPT that can immediately address a lot of your questions. And there's a lot of the way that mass specs are sold today is often based on the technologies they incorporate. And so, in order for vendors to tell you about how great their system is, they have to tell you what's in it. And so, there are now peer reviewed publications that talk about how different systems work and the technologies they contain. And so, it's often the answer when you're in grad school is go read the paper, right? And so if you can find the article that talks about the technology, you dive into that and you read it, you understand it. I would say don't be afraid to reach out to the authors. That was one thing that was a transition in my career is, okay, I can look up this paper and I can get everything I can out of it just by reading it. But you can go the next level because these are real people that are writing these articles, and don't be afraid to send them an email and say, hey, read your article, loved this, I had this question. And so information is really the key to getting to that next level understanding of how mass spec works and how you would develop it. And so that's the key skill is don't be the introvert that you want to be as a scientist. Don't be afraid to network and reach out and talk to people because that's how you expand your understanding. And not everything is written down. So having those conversations can be really meaningful and impactful.
Yeah, Daniel, I think that is great advice. I really appreciate all of your time today. Thank you so much for sharing all of this with our listeners. And I hope in the future we can sit down again to talk about how the adoption's going. And it was really great to learn about all this latest and greatest technology.
Yeah, I would love that. Thanks for the invite, David. I enjoyed talking to you and look forward to checking in 5 years and seeing how it's going.